Hey everyone! Welcome to Procedural Futuristic Design in Houdini through Rebelway. I'm so happy that you've decided to join me for this class. We really are going to have so much fun. This is going to be absolutely fantastic. So I apologize in advance. I've got to do a bunch of talking first before we get to the fun stuff in Houdini. So just bear with me. I promise it's going to be good information that we're going to use throughout this course and just to get everything set up nicely. So let's just get that out of the way first, and then we'll dig into Houdini in a little bit. So just a little bit about me right up front. My name is Russ Gauthier. I am a creative director, art director, designer, animator, and Houdini lover. I've been a Houdini lover for a number of years. It's so much fun to use. You can see more at robotastronaut.tv, or you can follow me on Twitter at robotastronaut_. So just a little bit of my background. For the relevant stuff, I have done FUI and title design for several features, including Spider-Man Far From Home, Black Panther, Thor Ragnarok, Batman v Superman, and a whole bunch of others. And you might be wondering, what is FUI if you aren't familiar with that term already? That stands for Futuristic User Interface, or Fantasy User Interface, or Fake User Interface. You just insert your favorite F word in there and it'll probably do the job. But really what that is those kind of visual storytelling devices you see in feature films. Think of like Iron Man holograms, or big command center full of like crazy information. It's really there to serve as kind of visual set dressing, but also really be a key storytelling element in so many ways. So that's kind of what I do. I also do title design. That's main title design, as well as title sequence design. I've done several of those as well, and those are always a lot of fun. But this class, we're going to focus on FUI. So I've, of course, been a Houdini user for quite a few years now professionally. I picked it up and really spent, a year dedicating myself to learning the program as much as I could before I started trying to bring it to the table professionally. And I love it. It's been so much fun. I've also taught Houdini at SVA to both graduate and undergraduate students in the computer arts department for a couple of years. That was a lot of fun. I've also served as thesis advisor for several of those students. So I really enjoy the academic process. I really enjoy teaching. It's something that I've always had a lot of passion for. But I'm also a longtime Cinema 4D and After Effects user as well. Like, I come from a very traditional graphic design background. I got into motion graphics in the early 2000s, and the tools of the trade are Cinema 4D and After Effects. That's the motion graphics bread and butter. Houdini really became a tool for the motion graphics artist only in the last few years. Like, it hasn't been a tool traditionally used in that industry. It's really been more for the visual effects industry, of course. But again, we'll get into that in a little bit. So what are you going to need for this class? Well, you're going to need Houdini, obviously, right? I'm going to assume that you have some familiarity with Houdini, that you aren't a brand new user. I'm not going to be going over any of the user interface or anything like that. This is not an intro course. That said, it's also not going to be like a super hard course. There aren't going to be too many things in here that we're going to cover that are like on the advanced spectrum of things. We're going to be working almost exclusively in SOPs. We aren't going to be doing any dynamics or anything like that. We're going to be using Redshift for our rendering. You don't have to, you can use whatever, but I'm going to be using Redshift, and if you have Redshift, it's just going to be easier for you to follow along and produce what we're ultimately producing here. I'm going to be using Adobe After Effects and maybe a little bit of Illustrator on the back end of this thing for compositing, for design, and that kind of thing. So you could totally use Nuke if that's something that you're more familiar with. If that's a tool that you have at your disposal, that's also totally fine. You could use Fusion if you want. I don't know anything about Fusion, but you could totally use it. But I will be doing everything in After Effects. So if you are on the newer end of the spectrum when it comes to Houdini, just a little bit of learning advice. I would avoid using the shelf tools, at least at first. There are a handful that you'd use, the camera and Redshift IPR and that kind of thing. But really for the most part, you want to avoid the shelf tools. They're basically just presets. And in a lot of cases, they end up creating a bunch of nodes and data that you just don't really need. So ignore the shelf tools, at least at first. Bite off small problems. Don't try and tackle everything all at once. Take it one step at a time. Just little baby steps will help it feel a lot less daunting. I like to keep a Google Doc of notes, and I still have a Google Doc of my own notes. It's more or less nonsense to anybody else because it's really just for me. I write it in my own voice. Like it's it helps me remember some things that I tend to forget. Nodes that have particular uses or ways that I solved problems in the past that keep coming up. So keep a Google Doc or some notes for yourself somewhere. It's just you'll reference them often. And then use Houdini every day, even if it's just for a few minutes. Even if you just fire it up and play around with it for a minute, use it every day. It's gonna help it stick. It really is a use it or lose it kind of a situation. So we're going to go over what I call course tenets, basically our course philosophy. What are we getting into here? Very first thing, we're going to treat this like a real world project, or as close as we possibly can to treating it like a real world project. That means organization, naming. We're going to get a brief. We're going to interpret that brief. We're going to go through a design process, the whole thing. We're going to treat this as if this were a real world project. We are going to build complexity over time. We aren't going to start off at full complexity. We're going to build this thing from scratch. This is going to be a very design-focused execution. So we are going to be discussing a lot about design. We're going to be iterating. We're going to be talking about making good design decisions. I will explain everything along the way. I'm not going to skip anything. You will see all of my process. I'm going to build this project from scratch, just like you will. And it's really going to be an honest look into my design process. If you're a seasoned artist, if you've gone through this process many times before, if you've been out there in the world for a while, the technical ins and outs of this course may or may not be super useful to you, but what is useful is always just kind of getting a peek at somebody else's process, how somebody else solves a problem. You get in somebody's head that way, and that can lead to some really interesting kind of personal discoveries that you can take with you and put into practice yourself. So if you're a seasoned pro, maybe this isn't the most technically challenging course for you, but I really hope that you'll get something out of at least seeing me go through the process. And then all of this really is in service of one goal, and that is to gain understanding, not just knowledge. I'm not just going to show you how to push the buttons. I'm not going to show you just which nodes to put where. We're going to talk about why we make these decisions, why this node works for this particular thing, why we're using Redshift, why. That's really what we're after here, right? So let's talk about Houdini for motion graphics. Houdini has traditionally been a tool of the visual effects artist, and really only in the last few years has it gained a lot of popularity in the world of motion graphics. This is for several reasons, but really it's studios like Man vs. Machine and Tendril and places like that are really kind of harnessing the power of Houdini for the motion graphics world, right? Traditionally, it's been Cinema 4D and After Effects and Maya. But Houdini has a whole lot to offer the world of motion graphics. It's a really amazing tool. So Houdini and motion graphics versus visual effects. Motion graphics timelines tend to be much, much shorter than your traditional visual effects timelines, right? So you may not be working on one shot or one sequence for months at a time. You might have weeks or even days to work on a shot. So you have a very short timeline usually. Sometimes you have a pipeline. If you do, they're probably really small, but you may not have a pipeline at all. You know, a lot of motion graphic studios tend to be really small. A lot of the teams tend to be pretty small, pretty agile teams. And a pipeline isn't, you know, every project tends to be different in the motion graphics world, right? It's not like a visual effects project where like, well, we're doing explosions for another feature film, or we're doing building destruction, or we're, you know, smashing cars, or we're doing oceans or whatever. You don't know what's coming in the world of motion graphics. So it's really hard to set up a traditional pipeline for that kind of thing, especially with small teams. And there's a good chance that you're going to be the only Houdini artist on that team, depending on where you work, of course. But chances are you'd be working with Cinema 4D artists or Maya artists, or you might even be the only 3D person on the team. So there's that as well. Proceduralism for design. So design is a very iterative process. The more you can refine your design, the better it's going to be in the end. And refining your design means that you have to design it and redesign it and redesign it and redesign it. This really favors a speedy approach, right? This is something that Houdini can have a really hard time with, especially in the beginning. So as you're getting your project set up, as you're getting your kind of recipes built, there's oftentimes a lot of time where there's no visual output. You're making progress, but you know, the people who are working with you may not actually see any progress. And that brings me to this point, which is setting good expectations, right? Especially if this is a studio or an environment where the Houdini process hasn't been really introduced before, right? Like if they aren't used to working with Houdini artists, it can be a little bit unnerving when you've got a really short timeline and you see an artist jamming away and making no real progress, right? So I like to draw what I call the Houdini progress curve for directors and designers and people on the team who haven't worked with a Houdini artist before or aren't familiar with that idea. This is the curve that I like to draw for people, just as a way of showing kind of what they can expect when they work with a Houdini artist for the first time, right? So I usually draw just a really simple graph, right? This is progress, and this is time, right? So when you're working with a program like Cinema 4D or Maya or something that is more traditional motion graphics tool, you tend to have a pretty linear progression over time, right? So like if you put in, let's say 1 hour, this is 1 hour, you would expect to get about 1 hour work out of it, right? So like if you're sitting down to model something and you've been modeling for an hour or so, or you're animating something, you would expect to see about an hour's worth of progress. Like if you came over to an artist's desk and said, hey, show me what's going on. You know, likewise, if you spent 5 hours, you would expect to see about 5 hours worth of progress, right? That's simple expectations, right? But when you're working with Houdini, there could be, and usually is, a whole lot of time where you don't see hardly any progress at all, right? Like you might sink a day or two even into getting a recipe built for something. And, you know, if a director or an art director is not used to working with a Houdini artist, this can be, you know, this would be a huge red flag for them. They would be like, what are you doing? Why can't I see anything? The thing is, once you get that recipe built, your progress curve does this, right? So it becomes something where you can get exponentially more progress out of your recipe. It becomes a very flexible tool. It just takes a lot of time to build that tool sometimes. Your progress curve isn't necessarily a linear one. And so I think it's really important to set that expectation for the people that you're working with if they aren't used to working with Houdini artists. So let's take a second to talk about when to use Houdini and when not to. So Houdini versus other programs, I kind of don't like to think about Houdini versus other programs. It's not one or the other. It's not one over the other necessarily. It's not one tool being better. It's just tools being used for what they're really good at. Tools like Cinema 4D and Maya are going to give you that very linear progress curve. That's going to be, if you have a day to sit down and design 3 style frames, you probably don't want to start that process in Houdini unless you absolutely have to. Houdini is going to take quite a bit more time to get up and running, unless you have some very purpose-built tools for whatever you're doing, or whatever you're doing can't be done in another program. Those really fast turnarounds tend to be a bit of a rabbit hole for getting started with Houdini. That said, if you have a style frame that you've got to do that's incredibly complex, requires a lot of geometry, or requires simulation that you just can't do in another program as easily, then Houdini is perfect for something like that. Likewise, if I were doing, say, like a 3D type layout, I wouldn't do that in Houdini necessarily, unless I were planning on doing something particularly Houdini-like with that typography. I would likely do something like that in Cinema 4D. Houdini is really good at repetitive processes, and especially when used in a pipeline or in conjunction with Cinema 4D, it can handle so much more geometry, so much more complexity and data. That's kind of Cinema 4D's weak point in a lot of ways. It's, I really like actually using them together. I do that quite a bit. I use Houdini and Cinema 4D, interchangeably in a lot of ways, especially early on in the process, like for design frames and that kind of thing. In this course, we'll be using all Houdini, but in my own process, a lot of times I'll dip into Cinema 4D for quick design elements, or to bring elements from Houdini in and mix them with things that I've done in Cinema and render them out. That's just my process. But the metaphor that I like to use is, if you need to build a chair, then you can do that in anything. There's no reason for you to do that in Houdini. Houdini's just going to take, it's just going to take just as long as anything else. Why not do that in a program where you can iterate on that really quickly? But if you need to build 100 chairs, 100 different chairs, you can do that really quickly in Houdini. You basically set up a recipe for what a chair is, and then you change your settings, change your attributes, change your data, and you have a different chair. You can do that as many times as you want. You can have 1,000 different chairs if you want. Where if you were going to build that in something like Cinema 4D or Maya, unless you have some very specialized tools, it's a very hands-on process. So it can be a little less efficient for that kind of task. So Houdini primary roles for motion graphics, at least what I've seen, certainly designed for particularly complex scenarios. If you've got design frames that you just can't get done in something else, or that you're going to execute the final shot in Houdini, you probably want to start the design process in Houdini. It's just going to make things easier as you go. And certainly it's fantastic for production level procedural animation, dynamics, and all kinds of complex animations and repeated processes and that kind of thing. Houdini is amazing at that. But Houdini also plays great as a support role in the world of motion graphics as well. I've used it for processing and pipeline stuff. Houdini has saved my butt on so many occasions over the years where you just have a problem that crops up that you just can't fix in anything else, or it would just take so long. It just feels so daunting. Houdini just has fantastic tools for support in the world of motion graphics as well. Tool building, if you're building a project that involves a lot of repeated processes, or you're using somebody, you're working with a team who's using Houdini Engine for anything, building tools from scratch in Houdini is fantastic. And then, of course, dynamics accompaniment, secondary animations, reactive animations, anything dynamic, of course, Houdini handles incredibly well. So let's get into what we are going to do for this class, the project itself, what we're actually going to build. We are going to concept, design, and produce a feature quality storytelling FUI element and sequence. We are going to start with a brief. We are going to develop the concept after interpreting that brief. That means we're going to make sketches. We're going to gather reference. We're going to talk about what we're going to build. We're going to brainstorm ideas. Then we're going to build our scene in Houdini. We're going to do this all in Houdini. We're going to design style frames. We're going to make motion tests. And then in the end, we're going to produce, render, and composite for final delivery. So we are going to assume whatever we are delivering is going to go to the director or the studio or whoever to be integrated into the feature film. Let's talk about the brief itself. So I'm going to really talk about this as if it were a real world project. You don't have to do that if you don't want. If you just want to take this as like an opportunity to learn some new nodes or see some process, that's totally cool. But if you want to treat this as a real world project that you are designing from scratch, you can do that as well. I want to give you that option. So I'm going to present a brief, and I'm going to use this brief throughout the rest of the class. This brief is basically going to be our groundwork that we're laying in the very beginning, and everything that we do, we're going to always look back to the brief and we're going to say, does it satisfy the requirements? Does it satisfy what the studio or what the director is looking for? Now, because we don't have a actual feature film project that we're working on, we are going to assume that this brief comes to us very early in the feature film project. So we don't have a plate that we're putting this on. We don't have an edit that this is going to go into. This is almost concept development in a way, but we're going to treat it as if it were going to be a real thing. So let's talk about the brief itself. This will be a feature film project. It takes place in modern times. So think Mr. Robot, kind of near future, current time technology. We're not talking like far future sci-fi stuff necessarily. The story beat we're going to be designing for, there is a malevolent rogue signal coming from North America that is infecting satellites in orbit with a virus, shutting them down or turning them rogue or, taking control of them, whatever you want to do. This is the very broad outline that we've been given. This is a high-tech government-style monitoring facility. That said, the exact location and technology used is TBD. Maybe the director hasn't figured that out. Maybe they haven't really written this particular story beat. They're just talking about it in the writing room, whatever it is. This is a scenario that has come up for me personally many, many times. There have been several instances where the studio I'm at or whatever has been brought in even before the script is even finalized, even before it's really written. to help concept a visual or to help design a story beat for a particular moment. That means that you could use a holographic projection. This could be a huge command center screen, sort of like, NORAD or NASA or something. It could be a small device like an iPad or like a phone or, some kind of like small hologram. Or it could even be like from an AI perspective, right? Like it could be entirely within the computer. And, maybe the story that you're designing for has, an artificial intelligence or that particular story beat takes place entirely in a computer and it's not really supposed to be for human eyes, whatever it is. That's entirely up to you. I want you to design what you're interested in, design for something that feels exciting to you. I don't want to dictate that to you. That this is your project. But what would be really useful is to have that laid out right here. So before you even continue any further, say like, okay, I'm going to design a hologram. That's what I'm going to do. It's going to be a hologram. It's going to be really big or it's going to be really small. Or what I'm going to do is for a flat screen. It's really important to have that perspective right in the very beginning so that you have sort of a target that you're going for, because that's going to dictate a lot of your design decisions in the future. I am going to proceed as if I am doing a holographic projection, but you can do whatever you want. So delivery specs for this, pretty simple. We're going to be delivering an overscan 2K, which will be 2156 by 1212. That's our delivery resolution, but we are going to protect for 239, which is 2048 by 858. And we'll get into that when we get into design frames and that kind of thing. We're going to be working at 24 FPS. We're going to be delivering a EXR sequence and a reference MP4. If you don't want to do that, that's totally fine. But this is a pretty typical basic delivery spec. A lot of times when you're dealing with a feature, you'll have a show LUT or anything like that that's gonna throw curveballs in your design process. We don't have that for what we're doing. We're just in kind of concept stage at this point, so we aren't worrying about any of those kind of things. We also don't have an edit, so we don't have any particular shot length that we're gonna have to hit. We don't have shot names. We'll probably invent a shot name as we progress. It's just going to help us keep our file names nice and tidy and keep things really organized. But in a real world scenario, a lot of times you'll be given an edit, or you'll be given a count sheet or something that's going to give you exact frame counts for exactly what you need to do. We don't have that. So let's talk about developing the concept. Where do you even start with something like this? Well, we're going to start by interpreting the brief. We've been given this very vague brief. We don't really have much to go on, no specifics. We don't know who's involved or, if there are people in the scene or whatever. All we have is this very vague brief to start with. So we're going to break down the important elements. What are the things that we need in order to start this design process? And we're going to do everything with the idea that telling the story as clearly as possible is the number one priority. That is always number one. So everything that we do, we're going to use this story beat as this sort of check for our design process. If it's helping to tell the story clearly, then it stays in. If it's muddying the image, if it's confusing things, if it's taking away from what that key story element is, it's out. So we're always going to use that. So let's start by actually interpreting the brief. I'm actually going to go back to the brief slide so that we can kind of see this. And I'm going to bring in just some notes for myself. And I'm just going to start by saying what are the things that I even need to do this, right? It takes place in modern times. So that's more context clues. It doesn't really tell me like what elements I need. The main story beat is this malevolent rogue signal coming from North America, right? So in order to have North America, I need an Earth or a map, right? So Earth/map of some kind. I don't know what that is just yet. But in my case, it'll probably be the Earth. We need this malevolent rogue signal, right? So we need some kind of indicator of the signal itself, some signal indicator, right? We definitely need satellites. So we need satellites in orbit. So we need some relationship between the satellites and the Earth, or the satellites and the map, or whatever it is. I think we're going to use an Earth. It would be pretty challenging, I think, to try and do this as a two-dimensional map representation and make the satellites make sense. So let's ditch this idea of it being a map. We're just going to stick with the Earth. But we need satellites in orbit, and we need a way to distinguish healthy satellites from corrupt satellites, right? So we need some way of knowing, like, okay, this satellite started off one way and then this rogue signal hit it and it turned to something else, right? Like, I need a way to communicate to the audience that a state has changed, a switch has flipped, something bad is going on. Cool. Beyond that, the rest of the brief here, the high-tech government monitoring facility, the exact location and technology used, that's, you know, kind of up to you. Those are more specific design things, and we'll get into how we can design those things as we dive further. But these, to me, are kind of the most important key elements in order to tell this story, right? Got to have all of these things together. So let's go back to here. So we're working on interpreting the brief. The next thing we're going to do is we're going to look for reference and real world examples. I really like to take inspiration from something that already exists, you know, like I'm pretty sure that there's no secret government satellite monitoring facility out there that's monitoring all the satellites in orbit. I could be wrong, but I'm pretty sure that doesn't exist. But there are plenty of things out there that do similar things, right? Like, think of like air traffic control or radar or anything like that. Those are things that we can start to look at for design inspiration. We can look at those kinds of things. We can also look at other FUI examples and things for some more like stylistic concerns. But I like to start by kind of grounding this idea in something that already exists. And then after that, we're going to sketch ideas. We're going to brainstorm. We're going to keep this really, really loose. You know, this could be writing treatments. It could be sketching ideas in a sketchbook or in Photoshop or whatever. It could be doing some really rough photo bashing. Whatever it is that you want to do, however it works for you to start to kind of visualize some of these ideas, craft some of these story beats. That's what we're going to do. So let's actually jump back to the looking for reference and real world examples. So I usually like to start with Pinterest. I've had a Pinterest account for many, many years. It's become a little annoying lately because like half of everything you see on the screen is probably an ad, which is super obnoxious. Like, I don't know why this stuff is on here, but you know, I guess Pinterest has got to make money somehow, right? So what I'm going to do is I'm going to start by looking for something more real world, right? So I'm going to start with, let's say, just radar. Helps if I spell it right. There we go. Okay. So radar is a great place to start. We can look at, you know, like there's something like this, which is kind of interesting. And I think we can, I don't even know why this is up here. because it's certainly not radar, but I think there's something to be drawn from here. So I'm actually going to make a Pinterest board, and I'll make this public, and you guys can come and check it out if you want. You can use this board for reference, or you can use your own, however you want to do it. But I'm just going to make a brand new board, and we're going to call this Rebelway. Rebelway, Houdini, FUI. That's going to be the name of our board. We're going to keep it. We're going to keep that public so you guys can check it out and see everything that I've got. But this is going to be our first pin, right? So I'm just going to grab this image, and the way that I like to use reference, particularly in the very beginning, is I almost look at this as an opportunity to have sort of an emotional response. Like, I'm not necessarily looking at all of the design elements in here. I'm not necessarily looking for something that hits all the points that I want. I'm really just looking to say, like, oh, like that caught my eye. That looks kind of cool. Sure, that's going into the board. I don't know if I'm going to use it or not, but like, I don't know. That's kind of cool. This is sort of interesting. Like, why not? This is going to get it's going in the pin. Sure. You know, I'm just going to go down the list here, and usually you'll hit a point where you like kind of exhaust some of this stuff. You know, like this thing. It's not the most interesting. I kind of like that idea of like the sweeping. What is this thing? That's sort of interesting as well, but it's, you know, I don't love it. It's not the most amazing thing I've ever seen. It's cool, but it doesn't quite hit the mark for me for what we're trying to do. Like, this is kind of cool. Like, that could be, you know, thinking about like this is like signals coming from Earth, right? Like, that's kind of cool. I'm going to throw that in the board. And I'm going to see, you know, one of the things I like about Pinterest is it shows you sort of other relevant images that are sort of vaguely related thematically to what you're already looking at. So we're going to look at like something like this, like, oh yeah, that's kind of cool. It's a little bit more FUI data stuff, so it's just not entirely relevant to what we're doing. This is pretty cool because there's a globe involved, and I see lots of little dots around, so that's kind of fun. I'm going to save that. We're going to look down here. Let's see, this is kind of cool, sort of glowy holographic globe. Lots of dots, like that's kind of cool. It's interesting. I'm not giving a ton of thought to this. Like, I'm not sitting here and picking out details. I'm really just looking to like grab things that grab my attention, right? And it looks like I've kind of gotten away from the radar imagery. Now I'm getting into like weird cosmic space stuff, which is cool, but like not quite what I'm after. So I'm going to go back here. I'm going to look for radar again. Now let's see what else we can find in the way of radar. I'm going to go here. Let's see what turns up under this. So like, this is kind of cool. This is this map of the northern sky. That's kind of fun. Sort of cosmically relevant. I have a feeling this is going to yield a lot of stuff that isn't entirely relevant to me, but this is interesting. Sure. Let's jump back. You know what? Let's do, like, this is pretty cool. Like, I love how utilitarian this looks, you know? Like, it looks cool because it looks like I would have to have like an advanced degree to understand what the hell is going on in this image. So like, that's kind of cool. That, you know, that kind of like raw utilitarian look is pretty fun. Like this is pretty slick. Like this feels like, you know, if I was looking over the shoulder, you know, like if you had told me that this was a screenshot of an actual air traffic control panel, I'd believe you. Like, that's pretty cool. I'm totally saving that. That's great. Like Like let's look at some other things that feel like kind of raw and modern. Like this feels a little dense, for lack of a better word. Like that doesn't really grab me, but this looks pretty cool. Like that feels really nice. Like you can imagine that these are perhaps individual planes or boats, or in our case it would be satellites, right? Like you've got a little icon and you've got a little name attached to it. That's pretty fun. I'm going to save that. I'm just going to go through here. Like this is pretty cool. Something, one of the things that radar always has is this kind of like sweeping line, right? Like this kind of thing. I mean, this is just a Shutterstock thing, so it's not that cool, but like if we look at other examples of that, like like this guy here, like I think that's kind of an interesting element, and not entirely realistic to think, because what this represents is, if you've seen any of those, the actual satellite, or I'm sorry, the actual radar hardware is physically spinning. So what you're getting is, this line represents that kind of line of information that's being returned to the user. So it's not entirely realistic to think that there's a spinning, global sized radar on the Earth, but it is kind of an interesting design element, and it's one of those things that people look at and go, "Oh, it's a radar. Duh. Yeah, I know what that is." So I'm gonna go ahead and save that because I think that's a relevant design element. That's kind of cool. Let's go down here. Let's look at some of these things. Like, okay, so that's just sort of nonsense. It's cool, but it's, sort of nonsense. Doesn't really mean anything to me. Now we're kind of into like 80s style, like retro graphics kind of stuff, which isn't entirely what I'm looking for. Let's try satellite radar. I don't know. Let's see what that turns out. Maybe nothing. Okay, lots of images. Like we've already saved this guy. What is this thing? This is some vector stock image of, some FUI nonsense, which doesn't entirely help me out. Not super duper relevant. Let's see what else. Okay, so this is kind of a rabbit hole. We don't really need to go down. This is kind of interesting, right? So this may be a visual representation of satellites in space. Sure, that's relevant. It's not beautiful, but it's kind of cool. It starts to hint at like the density of satellites around the Earth. Maybe something like this as well. Like, what is this? That looks like satellites in a grid of some kind. Like, again, not a beautiful image, but there's things in here that I think are really relevant to the communication of the idea of satellites floating around the Earth, right? So let's see what else. Let's see what else is under here. There's this thing. So this is kind of interesting in terms of like showing a signal, right? Like we get these kind of cones, but really it doesn't quite hit it, and it's not like I don't get excited looking at that. This is kind of cool. I mean, this is a weapon, right? It's sort of like a laser that's shooting down an airplane. But it's kind of an interesting idea to think about, like, what if the signal was a laser, right? So like, okay, sure, I'll save that. Why not? Let's see what else is down here. This is all gonna, this is just gonna military weapons in that slot, which is not the most relevant information. Let's see now, like observatories and actual spacecraft. Not super interesting to me for the moment. Let's see. Let's see what else is down here. This one doesn't seem to be yielding a ton. Let's go back. What is this? This is just some like stock image that kind of looks like a vector scope or something like that, which is not super duper relevant. This is kind of cool looking. What is this guy? Yeah, that's kind of fun. I don't know what the hell it is, but nope. There we go. Okay, we got it. Let's see. Let's see what this yields, because this feels like it's gonna send me down more of an FUI path, which, you know, we've got like a few examples of like radar and air traffic control and stuff, but we haven't done a ton of actual FUI. What is this guy? This looks kind of cool. I don't really know what it is, but it's pretty cool. So I'm just going to go ahead and save that. Rebelway, there we go. Yep. I don't know what that is, but I like it. It's kind of fun looking, right? This is kind of cool too. I like this. Save that. Kind of like those lines. Like same thing like this. I love like the density of these kind of images, right? Like this is just like, it feels really kind of techy and cool. Here's one of the Earth. Maybe this one has something. Nope, that's just some, looks like the background of like a cheap news broadcast. It's not quite what I'm after. What is this guy? That's slightly more interesting. I like that there are like these things kind of in space as the globe is spinning. So I'm going to go ahead and give that a save to the Pinterest board. That's pretty cool. All right, here's some more like FUI style hologram goodies. This one's got sound to it. There's some interesting things here. Sure, why not? We'll just go ahead and pin that. So what I'm doing is really just kind of going through and grabbing things that, you know, like they may or may not be ultimately useful to what I'm doing in the end, but they're things that have relevant stylistic elements or feel like they could be useful, and I'm getting a kind of immediate response about it, right? Like this is sort of interesting. This feels like, you know, like a swarm of bees or something, or a flock of birds rather than a map of satellites. But like there's something kind of cool about this stuff sort of popping up around. Like it feels like there's a lot of information here, which is kind of interesting. So I'm going to go ahead and save that. Why not? That's cool. Let's see. What is this one? It's a little bit more just generic point cloud. Not super interesting. Let's see what else we have. What else can we grab? All right, let's go back. Let's go back and look up air traffic control. Let's do that. Let's look at something like that. See what some actual air traffic control panels look like. I don't know that that's real. That feels like it might just be some fake nonsense. That doesn't feel super realistic to me, so I'm going to skip over that. Maybe we do air traffic control panel, right? Or screen. Yeah, that feels a little bit more interesting. Like this feels like maybe what we pinned earlier. Let's see what else. Down this way. Nope. Nope, more cockpit kind of stuff. That's not super relevant to what we're doing. What about this guy? That's just some nonsense, clearly. Like there's what about this? Okay, that feels a little bit more interesting, a little bit more realistic. I just love how like raw something like that looks. You know, like it doesn't look, it looks complicated. It looks stripped down. It looks really utilitarian. I'm going to go ahead and give that a save. That's cool. I dig that. Let's see, what else? What else is down here that we can start to look at that could be interesting? So, usually I spend a little bit of time digging through here. What is this? That's kind of an interesting close-up view. I'm going to pin that too. That's fun. Usually I spend a little bit of time just kind of combing the internet, and like, you don't have to stick with Pinterest. You can just download images off of Google or whatever. But I like to spend a little time going through and just kind of gathering some things up, right? Like, I'm not putting a ton of thought into each of these images. Let's go through and look at what we've got in here, right? So what I've got is a bunch of images, things that are just sort of disparate elements that are all loosely related to what I'm doing, right? Just these kind of like loose collection of images. Let's go through and talk about some of the things that could be relevant to what we're doing, right? So this is not a pretty image by any means, but what it is doing is it's very clearly communicating to me this idea of satellites orbiting the Earth, right? Like, I am not a air traffic control expert. I can't look at a screen like this and make sense of that as a audience member, as a member of the general movie-going public. I can't look at this and interpret what's going on. So I need help. I need somebody to show me what it is that I'm looking at. And a great way to do that is to introduce this idea of physically showing an actual satellite. Do we want to have, like, I don't know how many satellites there are, 6,000, 10,000, 20,000, who knows? Do I want that many satellites floating around? Probably not. That's going to be a big mess, but it's something to think about, because this communicates to me very clearly. It's gross looking, like it's not cool, but like it communicates, and that's a really important thing. So that's something I'm going to think about when I'm designing this thing. Thinking about the Earth, looking at like this image, right? Like, this image is pretty cool. It's a kind of dot grid of the Earth. I could see these things out here being satellites, kind of floating in orbit, or maybe this is data being transferred up and down, because, satellites don't just transfer data down to Earth. Of course, Earth transmits data back up to the satellites as well. So the data flows both ways. Like, I could see this being data moving around. The other really cool thing about this is that when this is moving, we're going to want to rotate the Earth. When it's moving, you're going to get a lot of like really cool, like kind of deep parallax, as those, like the points that are further away from the Earth move around. Like, you're going to get a lot of parallax, which is just sort of a visually impressive design element. So I like that image for that. I like this image for that as well. Like, this one starts to really talk about like I don't know, is that Australia? Like, what? I don't know. I don't even know if that's like a real Earth, but I can interpret that as the Earth, right? Like, I can think of that as the Earth, and I can think of this idea of maybe this like ring going around, or some kind of like a grid-like element to give me like coordinates in space, something to give me something to hold on to, some kind of structure, because I'm imagining that the satellites themselves are going to be very unstructured, very disorganized, and we'll see once we dig into it. But that's kind of my idea, is this, anywhere you can introduce this idea of contrast, the contrast between something that feels very organic and scattered compared to something that feels very ordered and regular. that's any kind of visual contrast like that is always going to be a point of interest, right? So like contrast with color, contrast with scale, contrast with shape, um, contrast with density. So I really like the contrast that's going on in this image. We have something that feels very regular and ordered, and these points that feel very scattered and organic. I think there's something really interesting to that idea. And that's an idea that I want to carry through into my final design. I already talked about why I grabbed images like this. It feels raw, it feels utilitarian, it feels stripped down. There's nothing fluffy going on here. It's not meant to look cool, but in its efforts to be purely utilitarian, it ends up kind of looking cool already. Like it feels real, which is interesting. So like, I don't know if this is a real air traffic control screen or not, but I could buy that it is. Me as somebody who's not an air traffic controller, I could look at that, and if you told me that that was a screen grab from somebody's terminal, like, okay, I believe you. Like, I totally understand that. It feels utilitarian, and that's something that we really want to communicate here, is that this idea of like utility. This is something real that a technician uses every single day. He sits down at a chair, he comes into a room, or she, or whoever it is, or this is a device being used by some a spy or a scientist or whatever. It is a tool that somebody could use. It's not just like a fluffy, beautiful image. And looking at something like this really helps kind of drive that idea home and give your design this sort of like thread or DNA of something that feels like it's grounded in reality. So let's look at some of these other ones here. This guy, I kind of just snagged this because it felt complex, like I don't know if that's as many satellites as are in orbit or even where they would go. Like this could be just junk, but this idea of differentiating satellites with color or shape, that's kind of an interesting one. That's kind of cool. Same thing with this image here. It's just showing satellites. I already talked about this sort of like radar sweep line, which I think is kind of an interesting thing, and something that your average moviegoer will look at and go, oh, I get it. That's a radar. I see the sweepy line thing. Cool. I understand. It's a trope. It's a visual device that has been used since like the beginning of time in the movie industry to tell you like you are looking at a radar screen. Cool. So we like that idea. And then there's some like FUI things that I think are kind of interesting. We talked about this idea of, parallax and having elements in space. So that's kind of cool. Okay, I feel pretty good about this collection of things to at least start with. So now that we have a bit of reference gathered, you guys can use the reference that I've found, but what I would like you to do is just take a little bit of time, dig up some of your own reference, find things that get you inspired, get excited about where this could potentially go, and gather those things for yourself. Then after you're done with that, take some time and do some sketches. I'm gonna do some write-ups. I tend to think a little bit better that way. My drawing skills are absolutely garbage, but I tend to do better when I can just write things down or talk them out or whatever. If you have somebody to talk ideas out with, that's awesome. Brainstorming with another person is incredibly valuable, and can really, in a lot of ways, unstick ideas, right? Like it's just super useful to have somebody to bounce ideas off of. Get into doing some sketches, get into doing some write-ups, take your kind of raw ideas and put them down somewhere so that you can see them, so you're committing them to paper at least. And then come back and we'll continue. All right, welcome back. Hopefully you've gathered some of your own reference. You've gotten yourself really inspired, really excited to build this project, right? So what we're going to do now is actually talk about this real world data that I've been going on about. So when I was doing some research for building this project, one of the things that I really like to do, like I said, is to use real actual information that's available to us. And so I was able to find on the Union of Concerned Scientists website, they have a database that's updated regularly of all of the satellites currently orbiting Earth, right? So like satellites that are old, satellites that are new. It's 2,666 satellites around the Earth right now. And so you can download this in an Excel format or text format or whatever. That doesn't really work for Houdini. Houdini wants a CSV format. But thankfully, from a Excel format, we can actually output that. And so you don't have to download this. I'll make sure that this gets supplied to everybody so everybody has the same thing. But this is what the Excel document ends up looking like, right? It's a lot of information in here. There's so much stuff. There's all of these individual satellites. There's, like the site says, 2,666 of them. Each one has a name, a country of origin, an operator, users, etc. All of this information. Then there's all of these like crazy technical things here: longitude, perigee, apogee, eccentricity, period, launch. It's nuts. And this keeps going. There's so much information here on these satellites from the Union of Concerned Scientists, which was amazing. This is an absolutely incredible resource. And so what I want to do is I actually want to start with this as the thing that's really going to drive our entire model that we're going to build, right? The thing that we're going to design on top of is going to start right here in this. So what I've done is output a CSV file, which is the format that Houdini wants. You can do that right here. Go up to File, Save. Maybe we do Save As. Yeah, Save as a CSV. So you can save it out as a CSV, and basically what that does is it turns it into basically a comma-separated document that ends up looking like this, right? So this is the same data, it's just organized differently and it's separated with commas and that kind of thing, which is, insane to us, but Houdini can read through this stuff no problem. So that's kind of what we're outputting for Houdini to read. So here I have a brand new Houdini document, nothing in it. I've arranged the panels kind of how I like them. I like to have my node window here in the middle and parameters, and I always like to have my geometry spreadsheet up as well as, of course, the viewport, right? Gotta have that. So I'm gonna go ahead and save this before I do anything else, so it establishes all of my environmental variables and everything. So we're just gonna go ahead and save this. We're going to make a new folder. Make a Houdini folder. We're going to call this RW SatDev 01. Okay. Hit accept. Great. So now that we have that already set, that should set our $hip and $hip file and all that stuff, all those environmental variables that are really nice to have. Those should all be set now. So, yep, we've got all of these set here. And we can build more, we probably will, but for the moment, that's just fine. All right, so I'm gonna just drop down a regular old geometry node, and we're gonna jump on in here. It should be noted that I am using Houdini 18, but I actually built the original project for this thing in Houdini 17. So you can totally use that if that's what you have. And I don't think there's anything that we're doing in here that would involve anything newer than, or anything older than like Houdini 15 or 16 if you're on an older version. So the node that we're going to use to bring that in is called table import. And it's this little guy. And you'll notice it's got this little Python symbol here. It's running some Python behind the scenes. So this is the table import node. And what this will allow us to do is read that CSV file and pull data out of it, which is super, super handy. So we need to very first, of course, point it to our CSV file, right? So I've got that here. I've gone ahead and exported this thing. We hit accept. And you'll notice that not a ton has happened. Let's see what we've got here. We just have 2,671 points, which is more or less the number of satellites. It's a little bit more, right? But what it's done is it's created a point for every single one of those pieces of data, essentially a point for every single satellite. I don't have any data over here yet, right? I only have position values, and they're of course all set to 0 because we haven't told it to do anything. But if we look at the properties here, you can see we haven't actually told it to do much of anything yet. So it's looking for, what column number to read. It's looking for, we've got this translator thing where we can translate date to seconds or latitude and longitude values to a sphere. We're not really going to use any of that because our values don't really translate to latitude and longitude as such. And I'll explain that in a little bit. But first, let's get through the rest of this. We can set a maximum value, but we're not too worried about that. We don't have millions of lines of data or anything like that. So Houdini can handle everything we're going to throw at it. It's asking us for a name, which right now is just P. So it's just creating a point position. The attribute type, and then the attribute length. Like, is that a vector attribute? Is it a single float value? Whatever that is. So what we're going to do, most of our values, if we look at these things, most of our values are actually string values. So if I bring back up that Excel document, you can see here, like if we look at this very first column, this is names of satellites and alternative names, right? So this is it's just string values. Most of these are string values. Obviously these over here, these are more having to do with like the speed of the satellite and the location of the satellite. And obviously we'll need to use that. But a lot of these are actually just string attributes. So let's just import this first column in here and see what we get. So we're going to come back. I'm just going to set this name. We're just going to set it to like test or something like that. We're going to do an attribute value string, and you can see that grays out the attribute length. And now that we've done that, you can see that that is the first column from our Excel doc, right? So it's imported the label column or the label row as well. So the very first point is called name of satellites and alternative names. So we're going to have to do something about that. But you can see it's echoing all of this here. So we now have a established connection between Houdini and our CSV file that's full of the data, which is super cool. All right, so now that we know we can get the data from the CSV file into Houdini as an attribute, we have to kind of understand what's going on in this document a little bit more. And this is where I kind of dug in really hard to try and figure out what some of these things are. Like, how do you use this data to tell Houdini where to put each satellite, right? So we can kind of ignore the names for the moment. I don't really care about the country of origin or the operators or the purposes or any of that stuff. I start caring about things right about here, which is the class of orbit. So what this is telling us is we have low Earth orbit, geosynchronous orbit, and then there's also a mid-Earth orbit as well, MEO for mid-Earth orbit. So there's essentially like 3 tiers or broad categories. And the reason I know that, if we go back to our Union of Concerned Scientists website, if we scroll all the way down here, there's some resources. There's a user's manual. And this is really useful for understanding some of the terminology, because I'm not a satellite expert. I don't know what I'm talking about, but I know that this database has the information I need. So this is how I'm going to figure it out. So I'm going to go in here, and this is actually telling us exactly what all of these columns are telling us. I'm going to start with this class of orbit, right? So this is telling us low Earth orbit, medium Earth orbit, or geosynchronous orbit. Those are the three broadest categories. And the low Earth orbit ones are the ones that are going to be closest to the Earth. Medium Earth orbit are a little bit further out. And then the geosynchronous ones are actually the furthest out, and they are totally locked to the movement of the Earth. The low Earth and the medium Earth orbit ones kind of move on their own. But those geosynchronous ones, those are the ones that are like locked in position with the Earth. Okay, so the next column I'm going to pay attention to here is this longitude of geo column, right? So what this is telling us is it's telling us for satellites that are geosynchronous orbits, this is the Earth longitude at the point over which the satellite sits in degrees east of 0 degrees, which is in Greenwich. So this is only for geosynchronous orbits. So anything that's a low Earth orbit or a medium Earth orbit is going to have a value of 0. So that's really important to know, because they are not geosynchronous. They are kind of consistently moving. But what this is telling us is where in the longitude of the Earth does this satellite sit over while it's because it moves at the exact same speed of the Earth, right? So that's a really important one to know. Let's look at what the next column over is. I think it's the perigee. So there's perigee and apogee, and these are two very different, they're kind of two sides of the same coin, if you will, and they really define what's called the eccentricity, or the degree to which the orbit is no longer circular. So this is telling us the perigee is the altitude above the Earth at the point of the orbit closest to the Earth, and the apogee is telling us the altitude at the furthest point. We're actually going to ignore those for the moment. If you really want to dig in and you want to make your orbits, with accurate eccentricity, please go ahead. But that's a little bit further out from what we're going to end up doing in this class. The next one, eccentricity, again, that's just a measure of how eccentric the orbit is. For our purposes, probably not super important. This one, the inclination, is super important. This one effectively defines, along with the longitude for the geosynchronous orbits, this is telling us where in space these satellites actually sit. So if we look at the inclination, this one here, the angle between it's the angle between the orbital plane of the satellite and the equatorial plane of the Earth measured in degrees. So if you imagine a huge disk coming out from the equator of the Earth, that's 0 degrees. And if you imagine the poles of the Earth, being a line through the center, that's 90 degrees. So what this inclination is telling us is exactly how far above, in relation to the equator of the Earth, how many degrees inclined is it, or declined, right? So we have positive values, we have negative values, we have values that go above 90%, right? So this is telling us 97%. That's actually going to push it just over the North Pole. The next column over is the period column. This one's also really important because this is going to tell us how fast the satellites are moving along their orbit. So it's the time required for a satellite to complete one full orbit of the Earth given in minutes. So you can see some satellites are moving really quickly, moving really fast at 95, where this one is moving really slow at 1436.03. So this is telling us just how quickly each of these satellites is orbiting the Earth. And that's what we're going to use to determine how fast they actually go. You'll see that the geosynchronous orbit ones all have pretty much the same value. And they should, they're locked to the Earth. So that's why we're seeing values of 1436 versus values like 94.7 or 95. So you'll notice that all of those geosynchronous orbit ones are all going to have that 1436 value. Okay, so now that we have defined which columns are going to be the really important ones to us, we just need to figure out how to get those back into Houdini. So I don't really care so much about the class of orbit. That's not really going to be data that I'm going to need because all of this other data is really just going to help me get there anyway. But what I do need definitely is to start with this longitude value here, right? That one I definitely need because that's going to help determine whether or not a satellite is a geosynchronous satellite or not. So this is column number 9. So let's go back over here to Houdini. I'm actually going to keep column 0. I'm not going to call it test, of course, though, because that's not really going to work. I'm going to call it sat name. So there I have sat name down, right? We are going to add another row. So I'm going to do another attribute here. And that's just going to add another interface level here so that I can import more data. So this one, we're going to do column number 9. This one is going to be float data. We're going to call this, let's call this geo long. Our names are just shifted over there. Okay. All right. We're good there. All right, so now that we've got geo long, that's going to correspond to our longitude for the geo, right? So that's going to let us know where around the Earth those geosynchronous satellites are going to sit. I'm not going to worry about perigee or apogee or eccentricity. I am going to worry about inclination, and I am going to worry about period. So we know that this one is column number 9, so that means that this one is going to be column number 12. So do another one, like this. This one's going to be column 12. We're going to call this INC for inclination. Take this down here. So that should match up with the values that we see here, and it doesn't because that's not column 12, that's column 13. Yep, there we go. My bad. Apparently I can't count today. So we are seeing, you know, our very first point, which is actually showing us across the top what our columns are. We can actually just delete those. We just throw in a delete SOP after this, and we just get rid of point number 0. Get rid of points. We're going to get rid of 0. So that way we don't have that one kind of in our way, right? So now we've got our geo long, we've got our inclination, we've got our satellite names. What is next on our list? We're going to need the period, which is this one. That's column number 14. So let's go up here. Let's add in another attribute. I'm going to bring this down. We're going to do column 14. This one is going to be period. We're going to reduce this attribute length down to 1 because we're going to need that. Great, so let's just make sure that that data matches up with what we're seeing in here. So that very first number is 96, and is what we're seeing here, 96.08, 95. Okay, so that all looks good to me. Okay, so now that we are back in Houdini, we have our all of our points created with all of the attributes that we need. We've got our, you know, all of our points that are eventually going to represent all the satellites. Right now, they're all just sitting here at world 0, right? Because we haven't told them to do anything. They're just sort of sitting there. So now it's time to think about how we're going to end up creating all of this. We don't have traditional geospatial coordinates that are available to us. We have this geo long attribute. So we have essentially a longitudinal attribute for things that are locked to the Earth. And then we have this increment, and we have a period attribute. And those are really the things that we have to work with. We don't really have much else. We don't have X, Y, and Z coordinates. So knowing that these things travel in an orbit, obviously that's going to be a circle, right? So I think what we can do is approach this as if we were just copying a bunch of circles around the Earth. And those circles are going to be treated a little differently depending on whether they are the geosynchronous circles or whether they are the non-geosynchronous circles, your low Earth orbit and your medium Earth orbit circles, right? So let's think about it that way. Like we're going to copy a bunch of circles around the Earth and assign those circles the properties that we have on these points. So we can do that a few different ways, but I think what I'm going to do is start by separating out the geosynchronous satellites from the non-geosynchronous satellites, because they're just going to have to be animated differently. They're going to have to be treated differently. They can look the same, but like the way that we're going to treat them is going to be different. So let's start there. So how can we separate out the geosynchronous from the non-geosynchronous? Well, we know that the non-geosynchronous attributes or the non-geosynchronous satellites have a geo-long attribute of 0, right? Because they don't, it doesn't make sense for them to have this geo-longitudinal attribute because they're continuously moving. They're not locked to the Earth. So anything that has a value that isn't 0 has to be a geosynchronous satellite. So let's do this. Let's drop down an attribute wrangle and let's set up a little conditional statement that essentially defines a group for us. So we're going to say if f at geolong doesn't equal 0, we're going to set a group geosync equals 1, just like that. So if you didn't know, you can set up groups like this syntax here, where you have @_group, and then whatever is after that is the name of the group, and you just set that equal to a 1 or a 0, because a group is essentially just another attribute. It's either on or off. It's either in the group or it's not. So you can see if I middle click here, now I have a geosync group with 545 satellites in it, which is great. That's what I want. So let's go ahead and physically separate those out. So I'm going to throw in a delete SOP, and I think at this point I'll probably end up splitting this into 2 streams. So set this to points, and we're going to do geosync as our group, but we're going to delete non-selected. So we're basically just isolating the geosynchronous group here, right? So now we've confirmed we have 545 points as opposed to our 2,670 up here. So we've separated those out. And if we look at our geolong attribute here, we should see no values that are 0. So, of course, we have these negative values, which we'll address, but we have no values that equal 0, which means we've eliminated all of the extra stuff. It's awesome. So now that I've got those separated, what I'm going to do is set up just a really simple copy to points operation here. So we're going to drop down a copy to points SOP. And what I'm going to do is copy just a regular old circle. If I can spell the word circle correctly. There we go. And let's look at this circle. This circle, right now I'm zoomed way out. There we go. This circle is sort of on the wrong plane, because if you remember correctly, the angle of incidence, that incidence attribute is measured from the equator of the Earth. So what I'd like to do is actually take this and make this a ZX plane, so it goes this way, right? Because that kind of represents the equator of the equator of the Earth more so than the default XY plane. So we're going to do that, and a regular old primitive isn't going to do it. I want to make this a proper circle, so we're going to go polygons. I'm going to set this the point number to 359 points. Which is a full 360-degree circle, because it counts the 0, of course. So we should have 300 and, yep, we're going to make this an open arc, and now we're going to have 360 points. Okay, look at that. Okay, so now what we're going to do is we're going to throw this in here. We're just going to copy all these to these points. So we're not going to see much change, except for the fact that now we have 545 polygons sitting on top of each other. So now we need to set the properties of these various circles to their various angles and to their various radiuses based on the attributes that we have coming in here. So the first thing we're going to do is we are going to establish this sort of angle of incidence, if you will. So that's going to be this, this attribute here, this incidence angle. So you can see that you have like one that's like 96 degrees. That's going to be like straight up and down. But most of these are below, I would say, 10. So here, 10.6, and then you have all of these down here that are like 0.06, 0.01, and then some that are just straight up 0. So most of these are going to kind of go around the equator, with some that are going to kind of flare up, and one that's going to go almost directly 90 degrees over the Earth. So that's what we're going to be looking at to achieve here. So in order to do that, what I'm going to do is I'm going to establish a couple of variables in an attribute wrangle. We're going to do this using kind of the native functionality of the copy to point SOP. The copy to point SOP takes a up attribute, so you can establish an up vector, and it takes a normal attribute so that you can establish like a forward facing vector, and then you can manipulate those on a per copy basis, and that's what we're going to do here. So we're going to establish an up vector. We're going to say v at up. We're just going to set that equal to 0, 1, and 0. So just pointing straight up. We're also going to establish a normal vector. We're going to say at n is equal to 0, 0, 1. So that's going to be a vector that points straight across. So if I look here and I turn on my normals, you can see we just have every single point has a normal that points along the z-axis, which is great. So now what we need to do is we need to actually rotate those vectors because that's actually going to rotate all of our points here, right? So just to show an example, I'm going to throw in a transform SOP, and we're going to rotate. Let's say we rotate here along the x-axis. Now, when I go to my copy to points, you can see all of my circles are now facing that direction. So this angle, because I have a up and a normal attribute established, this x-axis now controls the tilt of each of these circles. Awesome. Well, we can drive that with an attribute for sure via an attribute VOP. So let's go in, throw in an attribute VOP. We're going to jump in here, and what I'm going to do is use, just going to create a little bit of space there between these two. What I'm going to use is a transform matrix VOP, which is this thing here. Now, normally with this VOP, it's looking for a position value. Well, we aren't really interested in manipulating the position. We're interested in manipulating the normal. So what I'm going to do is, instead of feeding it a position, I'm going to feed it this normal vector. I'm going to plug that in there, and I'm going to take the output, the transform position, and instead of putting it into P, I'm going to put that into N. So now what this is doing is effectively the same thing as what that transform node was doing. So now, if you can see, as long as, as I'm changing the X rotation values here on the transform, it's doing the exact same thing that the transform SOP was doing. So we can drive that with an attribute, and the attribute we're going to use to drive it is this inclination here. This is the value, if you remember correctly, this is the value that that gives us the distance, the angle between the orbital plane of the satellite and the equatorial plane of the Earth measured in degrees, right? So we've already established that 0 is my equatorial plane of the Earth. So now it's just a matter of offsetting it based on whatever that increment value is, that incidence value. So I'm going to use a bind node to access this INC attribute here. So put INC in here. So now we've bound that in here. We now have access to that variable, that attribute. And what I want to do is I want to plug it into this rotation here. The problem is the rotation is a vector input, and this is a float. My incidence attribute is a float. So what I'm going to do is throw in a float to vector node. And I know that the attribute or the angle that I want to adjust is only on the x-axis. I don't really care about adjusting y or z. I only want to adjust x. So I'm going to take the output of my ink, my incidence attribute, and I'm going to plug that into the very first input, which represents the x axis. And I'm going to take the output of this, I'm going to plug it right into the rotation. And now we can see that these have been offset along that angle of incidence, which is awesome. Like, now we are driving actual visuals using the data from that CSV. It's really, really cool. Okay, this alone isn't going to cut it, but we're gonna make some adjustments here in a minute. But you can tell that the majority of those lines are at or near the equator, right? They're at or near zero, with only a few deviating significantly, and we do have that one that goes over 90 degrees. So we would fully expect to see one doing this kind of motion. And so this is behaving exactly as we would expect it to behave. Great. So the next thing that we're going to need to do is determine how far it is away from the Earth. And before we go too much further, I am actually just going to drop in a sphere to just kind of roughly represent the Earth. And I'm just going to rename this Earth. If I can spell the word Earth today. There we go. Okay. So it doesn't, you know, we're dealing with relative scales here. We aren't going like, you know, cosmic scale on this thing. So we're going to make this just a regular old polygon. We're going to, you know, give it a bunch of points. So we're going to shrink this down to, like, I don't know, let's call it 0.1. Okay, so that's enough to, like, give us a sense of where the Earth is, right? Now, I do want to set these, the other attribute that we're going to have to worry about is how far away they are from the Earth, right? What's the circumference? What's the diameter of these rings? And I know I said that we were going to skip apogee and whatnot in there, but that's totally wrong. We need either perigee or apogee in order to make this work. Because if you remember from when I was describing these, perigee is the minimum distance to the Earth along the orbit, and the apogee is the maximum distance along the orbit. And any of these values that don't match up means that orbit isn't perfectly circular. We're going to make ours perfectly circular just for the, you know, the sake of ease, honestly, and visually it doesn't make that much of a difference. But if you want to get in there and you want to add eccentricity to these things, by all means, knock yourself out. What I'm going to do is just take the apogee. I'm only going to take this. This is going to be my distanced attribute here. So we're going to come back up to my table import. I'm going to add another line in here. And let's see if we can figure out which one of these it is. So we know inclination. Let's see, it is 1, 2 behind inclination. So if we look at where inclination is, that is column 13. So it should be column 11. And we're going to call this, interesting, we're going to call this distance, or just dist for short. And I'm going to shrink that down to an attribute length of 1. So I don't know if I made this clear earlier or not, but when that attribute length is over 1, you can see it's creating other distance columns. And I think what it's doing is it's just reading neighboring columns, because what it's looking for is multiple distance values, and it's not finding them, so it's going to the next column over. This is just a float. We just have one attribute in this column, so we're going to keep it at that. Okay, so let's look at the distance attributes. So let's come down here. And, oh, wait a minute. Our distance attribute is 0. That's weird, because I'm pretty sure that the distance attribute should be significantly more than that for geosynchronous orbits. So here's our geosynchronous orbits right here, like this set. This apogee value is like 35,000, almost 36,000. But in Houdini, it's 0. which is super weird. So let's look up here. Let's go up above before we delete anything. So it is bringing in values, right? So it's bringing in 576.0, but it's not bringing in 35,700 and whatever it was, right? The reason it is not doing that is because this apogee, when it gets above 999, they include a comma. And Houdini doesn't like that. Houdini doesn't understand what a comma is, and it doesn't understand how a comma fits into a float value. If it didn't have the comma, we'd be in great shape. But because it has a comma, we're going to have to jump through some kind of annoying hoops in order to get this to work. So this is part of the issue of using a CSV. It's, it's built for readability. It's built for, for scientists and researchers and engineers and people to actually read this. And so the comma is a great function of that. But for procedural purposes like us, not so hot. So one way we can test this is we can make an entirely different attribute. Let's just test. We're just going to make a test attribute out of the same column. We're going to call this column number 11. We're going to call this test, and we're going to set this to a value of 1, and we're going to make this one a string. So we're going to come over here. So distance. So here you can see distance. All of these down here is 0. Let's go down here. Let's look at these, because these are all going to be 0. If I go over here to the test attribute, that's what it should be. It should be 35,793. But because that dumb comma, we got a problem. Okay, so let's figure out how we're going to do that, because that needs to be fixed. First of all, I know that my regular float attribute up here isn't going to work, and I want to get rid of this test attribute because it's just cleaner if we just get rid of that. So we're going to get rid of the test attribute. We're going to keep the name dist, but we are going to change this to a string instead of a float. Now the problem with that, of course, is that we can't read a string as a float value because it's being interpreted in a different way. We can't use a string to determine the distance or the circumference of all of these circles. So we have to turn that string into a float value. And in order to do that, we have to find a way to get rid of that dumb comma in there. What we need to do is we need to split this number up into its sort of two components, right? So its first component is 35 in this case for this number, and then its second component is 793. And then we need to stitch those things back together without the comma in the middle, and then turn that into a float value. The way we're going to do that is we are going to build an array. We're going to use a split function, and the split function does exactly what it says it does. It reads a string, and it listens for markers that we define, and it splits that string and loads the various pieces into an array. So before we continue any further, let's discuss arrays. This is an incredibly powerful tool. It's a construct within the world of programming. It's very ubiquitous. It's used all over the place. But what is an array? What is it really used for? So you can kind of think of an array as like a single row of an Excel spreadsheet. An array could have float values, it could have string values, it could have vector values. You can load up an array with whatever, but they're usually represented by square brackets. So in this case, I'm going to create a float array, and we're going to, we could throw in like 0.6 and then 1.25 and 720.0. Whatever it is, negative 0.47821. So there's an array of float values, and each of these values has an index, and that index starts at 0. So this is, 1, this is 2, and this is 3, right? So you can tell which one of these numbers you're referring to by the index. that you're using to refer to that number. So let's talk about this string array thing. Okay, let's go back to what we're going to use. So we've got our number 35,790. And we want to get rid of that. So what we're going to do is we're going to use the split function, and we're going to tell the split function we're going to tell the split function that the comma in this number is going to be the thing that defines the separation of values. So what we're going to end up with is we're going to end up with an array in this case where we have 35, and then we've separated that and we have 790. So these are two different values now. Forget the fact that there's also a comma in the array. That's not counted. So we end up having two strings. So this is a string array that's going to give us the string 35 and the string 790. And then we are going to tell Houdini to smash those things together and give us 35790 without the comma in it. And then we're going to turn that into a float. Okay, so back here in Houdini, we are going to do this as a point function in Vex. And I'm going to do this using attributes at first, just so I can illustrate the point. But we are going to ultimately end up doing it with Vex variables because it's going to save a little bit of space, a little bit of memory. But we're going to set this up first using attributes as an example. So I'm going to make a string array, and the way that you set that up is normally if you're going to make a string attribute, you would do s at, we're just going to call this test, right? Or we're going to call this test array. So in order to make this an array, right after the s and before the at, we need to add an open and closed square bracket. That's going to say to Houdini, oh, you want me to make an array of strings. I got it. So we're going to set that equal to this function split. And split requires two things. In our case, it's going to require a string, which is going to be our attribute, and it's going to require a string separator, which is going to be our comma. So our string attribute is dist, and that's going to be s at dist because it's a string function now. Don't let the numbers throw you. And then we are going to define our separator as a comma. And we're going to put that comma in quotation marks because it needs to be a string. Okay, so this is building our array attribute, and it's telling this dist attribute to split and put a new value in the array every time it sees a comma. Cool, no errors, so that's good news. Let's expand this out and let's see what happened here. So this test array is what I'm after here. So you can see what it's done is, so like here, the value, this number used to be 22,194, and now it is an array with the value 22 and then the value 194, right? So this is what the actual number used to be. This is now what's populating the array. Cool. So now what we need to do is we need to smash those things together. And what I'm going to do that, and to illustrate the point, I'm going to make another attribute. We're going to call this s at smashed array. Why not? It's fun. And we're going to set that equal to the two values, value 0 and value 1 in the array. So we are going to say s at test array 0, which is going to represent the first one. We're going to say plus s at test array 1. And that's going to give us this smashed array value here, right? So we used to have 22 and 194, and now we have 22, 194. Is great. It's still a string attribute, but we've removed the comma. The comma was the whole issue. So the very last thing we need to do is turn that into a proper float attribute. In order to do that, I need to make a float attribute. We're going to call this we're going to call it just dist float. just to differentiate it. And in order to turn a string into a float, you use a function a to f. And we're just going to put s at smashed array. Spell it. There we go. Okay. So now we should have a dist float attribute that is the same thing as dist, except now represented without the comma as a float value that we can actually use, which is great. Now I'm going to go through here and clean this up because what we've done is we've actually created significantly more data than we actually need to create. We can do these 2 lines of code here using vex variables instead of using attributes. I was using attributes so that you could see what the actual output of the values were, but I'm going to reorganize this so that it's using variables, which uses far less memory. So the very first thing I'm going to do is I'm going to come up to this here, this attribute that we made, and we're going to rewrite this as a string. So we're going to call this string test array, and this is where vex is a little funny. You actually organize a new variable array like this instead of doing it the sort of weird way that they want you to do it with the attribute. So instead of calling this test array, because that's not very descriptive, we're going to call this string dist array. Or let's call it string split array. Okay. So down here, we also need to get rid of a handful of things here. We're going to say, instead of s at test array, because that's now gone, we're going to call this string split array. Same thing here. String split array. And I'm going to just click out here and we shouldn't see any errors. We don't, hooray, that's good news. We still have our dist float attribute and everything is working well. So now I can move on to getting rid of this attribute here because we also don't need this one. This one can be, I'm going to go string. We're not going to call this smashed array. We're going to call this split combined. Doesn't really matter because it's not going to be viewed anywhere else. And then we're also going to get rid of that down here and we're going to call this a split combine. And now we're going to test. Cool, no errors. We have our distance float attribute and we've gotten rid of our weird like test attribute things that we didn't really need. And we have exactly what we want, which is this, this distance value as a float and not as a string. So we can actually get rid of the string attribute now because we've got everything we need as a float. So we're going to get rid of dist just like that. Okay, so now we can come back down here to this area and we can introduce this distance value, which, you know, these values are pretty significant. You know, we're dealing with like 35,000 and greater. So I might want to scale that a little bit. And what we're going to do is we're going to do that right in here into this attribute wrangle where we define the up and normal attributes. We are going to define a p-scale attribute. And this again is one of those kind of built-in functions into the copy to point SOP where if you pass it a p-scale attribute, it will change the scale of the various copies based on that attribute. So we're going to do that here. We're going to say at p-scale is equal to f at dist float. Now, if I just leave it like that, we're going to get massive values. These things are still here, but they are huge. So if I zoom out here, yeah, you're seeing 78,125 meters. That might be, you know, more physically accurate, but for artistic purposes, for what we're doing, not going to work so well. So I want to scale that value so that I have control over exactly how gigantic that's going to be. So I'm going to throw in a, I'm going to multiply this times a channel function, just so I can have a little slider. So we're going to do CHF for channel function, and we're just going to call this AMT for amount. Okay, and then we're going to hit this little guy over here, and it's going to create our little slider, which is great. Look at that. Okay, so let's zoom back in here. You know, we're still seeing some pretty monstrous numbers. Let's maybe scale that down to like 0.05 or something like that. But now I have control over that, which is great. So this is going to give me my geosynchronous orbits. And next we'll define the actual position of the satellites as well. Okay, so next we need to define the points that are going to represent the satellites. So each one of these circles currently represents an orbit, or in this case, because they're geosynchronous, it's not really an orbit, but it's more of a location along a curve. But what we're going to want to do is, for each of these circles, we're going to want to create a single point that represents the satellite that is in orbit. Okay. In order to do that, what we need to do is we need to delete out all of the primitives. Right? We're gonna keep the points. We're gonna delete the primitives. So we have all of these, and then for each of those primitives, for each circle, I'm just going to remove all the points except for 0.0, because that seems like, you know, every one of these has a 0.0. So I'm just going to do that. But in order to do that, I'm going to need a way of doing this function on each of these individual circles. And in order to do that, I'm going to use a for each loop. So we're going to drop down a for each primitive loop right here. And what this is going to do, I'm just going to plug this in here. If you haven't used these before, these are awesome. They can be a little tricky to get your head around at first, but effectively what we have here is we are doing the same function. Whatever functions we put in here, whatever SOPs we put in between these nodes, is going to be done to each of these 545 circles individually, as opposed to doing them to all of them together. So we are going to delete out all of the points. I'm sorry, all of the primitives, and we're going to keep all the points. So now we have just a bunch of points. And then I'm also going to throw in another delete SOP, and we're going to delete out all the points except for 0.0. So we're going to say points, and we're going to say 0, and we're going to say delete non-selected. So now all we're left with is all the points that were previously 0.0 for each of those lines. The reason I did that is because now we are going to define the position around that circle that each one of those points came from. We're going to define that using this geolong attribute. That's going to be the attribute that's going to determine how far along the longitude of the Earth each of these points sits. And what I'm going to do in order to do that, I'm going to use a UV attribute. And I need to actually put that UV attribute on the circle here before it even gets copied to the points. So I'm going to go back up to this circle. We're just going to look at that. Turn off all of these. There we go. So I'm going to throw in a UV texture. It's one of these things that I use so often, I take it for granted in Houdini, but the idea that you can apply a UV attribute to a two-dimensional line is absolutely amazing. I absolutely love, I love this functionality. So what we can do is we use the UV texture SOP on the circle. We're going to change the texture type to rows and columns, and we're going to change the attribute class to points. And what it's done is it's created a UV attribute, UV X, Y, and Z, over here on my circle. We can see that if I throw in a color SOP. we can color this. We can change the color type to ramp from attribute, and we can set the attribute to UV. You can see what it's done. This is 0 over here, and it goes all the way around to 1. So it's this UVX attribute. The UVY and the UVZ attributes, they don't matter. They don't matter at all because we don't have a Y or a Z value. It's essentially a one-dimensional object. So we have a UV attribute, and we are going to use that to define where the position is of all of these points. So right now we have just a bunch of points sitting out in space somewhere. Where'd you go? There we go. Just a bunch of points sitting out here doing nothing. And we want those to be mapped to that circle. So we're going to use an attribute VOP for that. And I'm going to drop this attribute VOP over here so that the points are coming into input number 1. And I'm actually going to take the output of this for each begin node, and I'm going to bring that into input number 2. And that's because that's going to be the input where we actually read the UV attributes off of the circle to define the position. So let's hop into the attribute VOP here. The node that's going to make this all work is the prim UV node, which is just primitive attributes. And this node is super, super cool. What it does is it takes a UV attribute and it outputs whatever attribute you want from the position on the geometry at that exact point in the UV. So in this case, we are going to be looking for the P attribute, and we're going to be reading the geometry coming from input number 2. We're going to put that into our file input here. And the reason I say that, that's this input here. That's effectively our circles that are coming in. So we're going to be reading the UV attribute off of that, and we are going to be outputting the result of that over here to position. Now, when I do this, it's not really going to do much. This isn't gonna, well, it's changing things, but it's not changing them very well. How about that? What we want is we want to pipe a value into this U input. This is the number that really matters. The input we're going to want is this geolong attribute. So we're going to, again, bind in the geolong attribute. We're going to take the output of that and we're going to pipe that right into the U. Now, the problem with this is that this geolong attribute is in degrees. So if we look back up here, or even back up here, let's go back up here. This geolong attribute is in degrees. We've got everything from negative 179.8 all the way up to 328.5. But a UV attribute only goes from 0 to 1. So we have to tell Houdini to remap those values into a 0 to 1 range so that it understands where along the circle it is, because it doesn't know where a UV attribute of 328 is. We have to tell it that. The other thing we have to do, because we're dealing with a UV attribute, we don't want negative numbers. That's not really going to work for us. Negative numbers, the UV space is always a positive space. It's always 0 to 1. It doesn't really go negative unless, of course, you're dealing with texturing and everything. But what we're dealing with is 0 to 1 space. So in order to address that, what I'm going to do is actually come way back up here, and I'm going to redefine this geolong attribute. I'm going to say anything below 0, because we're just dealing with a circle. So, you know, if you think of like a negative 180 and positive 180, they're the same thing. It's the same position in space because it's just a position along a circle. So I can flip all those numbers and make everything positive and still keep the same positions. But I'm only going to do it on the negative values. So I'm going to set up another if statement here that says if f at geolong is less than 0, what I'm going to do is set the attribute f at geolong equal to 360 plus f at geolong. Now, that might seem a little weird at first, right? Because geolong, if you're adding 360 to it, it's going to give you values greater than 360, right? Well, we're only dealing with the negative numbers because this if statement is saying any number that's less than 0, do this. If it's greater than 0, it's ignored and it's passed over. So when you're adding a negative, you're actually subtracting, if that makes sense. So what that's going to give us is it's going to give us geolong values between 0 and 1. Right, so we have plenty that are 0, but we no longer have any that drop below 0, which is perfect. That's what we want. We now have values between 0 and 360, no more negatives. Okay, so let's go back down here to our for each loop, and we're going to see if we can address this here. So we've got this geolong attribute. This is numbers between 0 and 360. We want to remap that to 0 to 1. So we're going to do that using a fit range node. I'm going to drop this in here. And the fit range node just takes an input and it gives a source min and source max, and it outputs a destination min, destination max. So destination is whatever's coming out of the outside. So we're cool 0 to 1. We're going to leave that alone. The source min and source max, we're going to leave the source min 0. We're going to change the source max to 360 degrees. Now you can see what we've got going on. That looks way more interesting. And it looks like it's going all the way around the circumference, which is really cool. So essentially what we're doing is we're mapping degrees to a UV space, which is just 0 to 1, normalized. Cool. Okay, that's great. Okay, that takes care of our geosynchronous satellite placement. If we want, we could even merge these things together. Or, you know what might be even better is to just template this so you can see like all those points actually do sit on all of those lines, which is super great. All right, next on the list is the non-geosynchronous satellites. Let's go and take care of those things real quick. So we can use a lot of what we built over here on this side, the geosynchronous side. We can reuse a lot of that information and a lot of those nodes and a lot of those ideas on the non-geosynchronous side. It's really the same kind of thing, just a little different. So I'm actually going to take this chunk of nodes and I'm going to alt drag it and just copy it over. And so here for this delete SOP, instead of deleting everything that's not the geosync, we're just going to delete the geosync. So we have everything else. So now we have 2,125 points, where over here we had 545. Cool. So same thing. We can look and see what this is going to give us. It's going to be pretty crazy at first. Now, I took a little bit of artistic liberty with this and had decided kind of early on that having these monster rings out here wasn't really working for me because it's only a handful of satellites. The vast majority of these satellites are actually like in here in these inner rings. So what I'm going to do is I'm going to look at this dist float value, and we've got some that are really, really big, like 330,000. That's huge. Most of these are significantly smaller than that. Here we're down into like 1,500. You know, we get up to about 10,000 here. So what I'm actually going to do is I'm just going to throw in a delete because really we only have like just a handful that are massive, and they're going to kind of screw things up for us, I think. So we may bring them back later, but I think for the moment I'm going to delete them. So we're going to set this to points. We're going to delete by expression. We're going to say at dist float is greater than 10,000. Let's try that. Okay. That's a little bit better. We still have, you know, almost 2,000 satellites here, which is super cool. Like, that looks great. That's going to be That's going to be really fun. And these are the ones that are going to animate independently based on that period attribute, which is pretty cool. But this seems to work pretty well. I'm into that. So let's get rid of the grid for the moment. The next thing I'm going to do is copy over this for each loop, because this loop, this is kind of what defines where the satellites are positioned. And that's more or less what I want to do here. We're going to just do that a little differently, because the geosynchronous versus the period animated ones are going to require a little bit of a different approach. So first of all, we don't really have that geolong attribute because those are all set to 0 because we're dealing with non-geosynchronous satellites. So a lot of this can actually go away. What we're going to do is we're going to delete these two here. We're only going to leave this one that's just deleting out all of the primitives and just leaving us with the points. So now we have no primitives. So what I want to do is, because all of these are kind of animating randomly, we don't know exactly where they are or where they started. I can feel pretty confident in just randomly deleting all of the points except for a random point per orbit. So we're going to throw in an attribute wrangle, and we're going to wrangle that up. We're going to say if we're going to define a random number, so rand, and we're going to define that based on the primitive number. And what we're going to need to do before that is to establish the primitive number, because I've deleted all the primitives at this point. So let's do that before we continue. We're going to throw in an attribute wrangle before all of this. We're going to make a new attribute, a new point attribute called I at original prim, and we're going to leave that equal to at prim num. Just so each point knows, even if the primitive is removed, it knows what the original primitive number was. We're going to use that value down here. So we're going to say if, and make a random number based on I at original prim. So every point along that primitive will have the same random number because it's got the same random seed. The reason we're doing that is because we want to define one point that satisfies our if statement and remove all of the others. So we just get like a random point along each of these circles. We're going to say if that is not equal to at ptnum, our current point number, we're going to remove the point. The point that's coming from input 0 and at ptnum. So one last thing we need to do, because this random number is going to give us a value between 0 and 1, so it's going to be a float value. We're going to need to multiply that times 359, 360, right? And we're going to need this value to be an integer. So we're going to put this into a, all of this into an integer. So what that's going to do is it's going to remove from every single one of those primitives, it's going to remove all but one random point. So we should have at the end here the same number of points as we had primitives. So we have 1,953 points, and up here we had 1,953 primitives. So we are indeed dealing with 1 point per primitive, 1 satellite per orbit in this case. So now we need to make those things move. We're going to do that outside of the for loop in this case, but we are going to use an attribute vop for that. So we're going to throw in an attribute vop. We're going to approach this very much like we approached the other one, the geosynchronous orbits. But this one's going to require a little bit more because we're dealing with this period attribute now. So we're going to hop inside here, and we're just going to get these things wired up. So to show you what's going on here, I'm going to use the prim uv, this primitive attribute node, And we're going to wire this up exactly like we did before. We're going to take the op input 2, we're going to throw that into the file here. We are going to get rid of this CD attribute. We don't need that. We need that to be P because we want the point position. The other thing we're going to want to do is we're going to want to know which primitives UVs we should be looking at. And we have this prim input and we have prim number over here. The problem is we have no primitives. So we're going to need to bind in that original prim attribute, and that's going to be an integer, and it's just orig prim, just like that. So this is going to give us the primitive number that we're going to need to look up the UV attributes. So we're going to take the output of this, we're going to throw that into prim, and we're going to take the output of this, and we're going to wire that into P. Okay. Well, that looks a little weird, right? So let's move this U coordinate, right? And you can see things are happening. It's a little weird looking, but things are definitely happening. So we're going to need to do a handful of things here. The first thing we're going to do is we are going to add in a random offset value so that we don't end up with like straight lines, right? Like this doesn't look at all like what you would expect satellites orbiting the Earth to look like. They would all run into each other. It would be a mess. There's no way that they're all going to end up in a line. So we're going to want to randomize those a little bit. So I'm going to throw in a random node, and I'm just going to add that value into, we're going to create a random offset for that U. So I'm going to create a constant. I'm just going to make a constant value here. We're going to add a random number based on the original primitive, and we're going to feed that into our U input here. Now you can see we've got something that looks a little nicer, right? So now if I start moving this, you can see that all of these little satellites start animating around. And if let's see, maybe I can template these so that we can see maybe a little more clearly. Let's do this. Let's do a random color, and let's do this. We'll just do a random color based on primitives. So each of these primitives is going to get a random color assigned to them, and we're going to come back down here. I guess it didn't, whatever. Okay, so you can see all of these points are indeed animating along their respective primitives, which is great. But we're going to run into a little bit of a problem. I'm going to turn this off so that we can see what that problem is. The problem we're going to run into is that as these numbers start to approach 1, again, UV values go from 0 to 1. It doesn't know what to do with any values greater than 1, so eventually they're all going to end up in a weird line anyway. We need to tell it that we want it to, when it reaches a value of 1, to loop back to the very beginning. We're going to do that using a modulo node. And what the modulo node does is it effectively, it's the remainder of a divide operation. So it's going to divide by whatever number you put in here, and it's going to give you the remainder. We're actually just going to leave it alone. We're going to leave it at 1. So I'm just going to plug that in here. And now I can just animate this all day long, and they're just going to always continuously loop, because every time they get to a value of 1, they just loop back to 0, which is what we want because we've got a circle. Okay, so the modulo function totally solves that problem. Our random offset totally solves that. So now what we want to do is we want to get rid of this constant input. I don't want to have to animate this thing. I want to use the period data, that period attribute that's coming from our CSV file. I want to use that in place of this thing. I don't want this here anymore. So I'm going to bind in our period attribute, which is just PER, should be this guy here, right? Remember, this is the number of minutes it takes for the satellite to orbit the Earth. So we're going to bind in PER, and I like to throw in a fit range, just because that's always a nice thing to have. I don't know that I'm going to use it, but it's one of those things that I like to have in there. And I like to, let's throw in a multiply, because we're going to want to multiply whatever the output of this is by time. So we're going to take time and multiply those values together, and then we're going to replace that constant. So we're just going to get rid of that constant altogether. Let's go in and organize this a little bit so we can get rid of some of these weird issues we've got. Okay. Yep. That's cool. Great. So now if I scrub the timeline, those things are flying. They are going crazy fast. So I'm going to want to multiply that time value down a little bit. And in order to do that, what I'm going to do is just promote a parameter. I'm going to call this time mult, something like that. That's fine. And so right now it defaults to 0. So of course it's multiplying by 0. We're not seeing any movement. So we're going to go out here. We're going to go to my attribute wrangle, or I'm sorry, my attribute vop, and we're going to change this time mult value. Let's change it to like 0.1. And let's see what that does. Cool. Look at that. We've got all of those things animating along. They all do actually animate along their respective paths, because we're using the UV attributes defined by all those paths. So now we've got satellites orbiting using their orbits, which is just awesome. That's so cool. All right, the last thing I'm going to do is actually just start to merge some of these things together here. So we're going to throw in a merge SOP. We are going to merge in the geosynchronous and the non-geosynchronous satellites, and we are going to merge all of the orbits, because I want to have access to all the orbits. Now the orbits, I am just for the moment, if for nothing else, just for visibility, I'm just going to randomly color the orbits. I probably won't render them out that way, but for the moment, I'm just going to randomly color them just so I can see them a little better. And then we're going to group these up. So we're going to throw in a group SOP for all of the satellites. These are, we're just going to call this sat points. And we're going to make this group orbit lines. Great. So now we have all of our satellites defined, some of which are animating, some of which are geosynchronous, and of course we'll animate the globe in the next class so that we can get all of the geosynchronous ones animating as well. But I know I just dropped a ton of crazy technical stuff on you guys, and I want you to get up to this point and have plenty of time to understand what we're doing before I start adding more layers on top of this. So I'm actually going to stop right here for the week. What I would love you all to do is to get up to this point. I'll make sure that you're supplied with the CSV, and if you want, I'll give you the Excel document as well, so you can crack into that and take a look at that. Get up to this point, and then next week we are going to take this and we're going to finish our kind of basic animation so that we have what's effectively a canvas onto which we can start actually designing, because this is just kind of laying the groundwork. We haven't even started designing anything yet, but we need to get through this step so that we can start figuring out what the satellites look like and how they're going to move, and we can start figuring out like camera placements and that kind of stuff, so that we can like really start designing style frames. So get to this point, continue to work on reference, on any sketches, on any ideas. Feel free to hit me up in the Discord. I will do my best to be as available as possible to you guys. But things are busy these days, so please be patient. I promise I'm not ignoring you if I don't get back to you immediately. But we are here to help you understand all this stuff. So please stay in touch. Thank you again so much for joining me on this class. It's going to be a lot of fun. Talk to you guys soon.